Hello, welcome to another module in this massive open online course. So, in this module let us start looking at single sideband modulation, which is also abbreviated as SSB. Alright. So, what we want to start looking at is basically we have looked at double sideband modulation already, that is DSB-SC, double sideband suppressed carrier. Let us now start looking at single side band, which is also termed SSB, correct. Single sideband modulation, which is also termed as SSB. Okay, SSB stands for single side band. Alright, we have looked at double sideband in which both the sidebands are transmitted, correct. Let us now start looking at single sideband modulation. For this purpose, consider a message signal MT. Alright, so let us start by considering a message as usual. And let MF denote its Fourier transform, that is MF is the Fourier transform of MT, correct. We have a message signal MT and its Fourier transform given by MF. Okay. Let us draw this schematically over here. We have our message signal, MT. I am drawing the Fourier transform. So, let us say the Fourier transform is between minus Fm, it's minus Fm to Fm, where Fm equals the maximum frequency of, or the maximum frequency component, correct. We also say that the base bandwidth, so this is your spectrum MF of MT, in fact this is the baseband spectrum, and we also say that the bandwidth, the baseband bandwidth, the bandwidth of this baseband signal, which is the one sided bandwidth of MT equals Fm. Okay, this is also known as the one sided, one sided bandwidth of the. Okay, so as usual we are considering the spectrum MF with maximum frequency component Fm, that means it spans from minus Fm to Fm. All right, the one sided bandwidth of the signal of this baseband signal is Fm. Okay. Now, consider the modulated signal. Let us again start by considering the modulated signal. Consider the modulated signal xt equals our double sideband suppressed carrier signals, that is modulated by cosine 2 pi fct, where fc, remember this is the carrier frequency, mt is your message signal, xt equals mt cosine 2 pi fct. Therefore, this is a multiplication of two signals in the time domain. Therefore, the Fourier transform f x f is given by the convolution of MF with that of cosine, the spectrum of cosine 2 pi fct, which is basically impulse of scaled by half at fc plus impulse scaled by half at minus fc, that is delta f, half delta f minus fc plus half delta f plus fc. We have already seen this spectrum is basically equal to half MF minus FC plus half MF plus FC. This is the spectrum of the modulated signal. Now, if you look at the spectrum of this modulated signal, and we have already seen this before, that is going to look as follows. That is going to comprise of MF, we already seen this, shifted multiplied by a factor of half and shifted to FC. So, this is FC plus FM and FC minus FM symmetric about, correct. And now, if you look at this, there is going to be another component which is between, this is MF plus FC, this is on the negative frequency side, that is from FC or minus FC minus FM to minus FC plus FM, all right. So, the spectrum of XF, where your XT equals the modulated message signal, that is MT cosine 2 pi FCT. And if you look at the bandwidth of this signal, that is MT cosine 2 pi FCT, this is known as the pass band bandwidth, that is the spectrum occupied on the positive frequency side by this pass band signal. The pass band bandwidth is 2 FM. The pass band bandwidth of the modulated signal equals 2 FM. That is also the spectral band occupied on the, that is a spectral band that is occupied by this positive by this pass band signal on the positive frequency side. Alright. So, this is the double sideband, and remember this is a double sideband modulated signal because it comprises of two sidebands. And what are the two sidebands? We have already seen this. These two bands, if you look at between minus FC to minus FC plus FM, FC minus FM to FC, FC minus FM to FC, this comprises the lower sideband or LSB. LSB equals the lower sideband. And the other two bands, that is minus FC minus FM to minus FC and FC to FC plus FM. Now, these two, okay, let me just draw this separately. These two bands, if you look at these two bands, which I am drawing by this orange color here, these comprise the USB, which is basically the upper sideband. Upper sideband, the acronym for that is USB. So, we have the upper sideband and we have the lower sideband. Just to write it down clearly, we have the LSB, that is equal to the lower sideband, and that comprises of the intervals minus FC to minus FC plus FM union together with FC minus FM to FC. This is the lower sideband, that is minus FC to minus FC plus FM to FC minus FM to FC. Then we have the upper sideband, that is denoted by USB, that is equal to the upper sideband, and that comprises of the bands minus FC minus FM to minus FC union FC to FC plus FM. So, we have two sidebands, we have the upper sideband, we have the lower sideband of the signal, correct, and we have the upper sideband of the signal. Now, let us try to draw these two signals, these two spectra separately, that is the lower sideband, the upper sideband and the lower sideband. So, naturally the lower sideband spectrum will look as follows. This is going to be the lower sideband of the spectrum is going to, or the upper sideband of the spectrum is only going to include the upper sideband. So, if we only include the upper sideband, that will be, so that will be this is from FC to FC plus FM minus FC, and this is minus FC minus FM. So, this is going to be your minus FC minus FM to minus FC, correct. So, something like this is from minus FC minus FM. So, this is the upper sideband spectrum. So, this is your USB or your upper sideband spectrum. And now, if we include only the lower sideband, that will give me the LSB spectrum. The LSB spectrum will look something like this, that will contain the lower sideband. So, that will be minus FC to minus FC plus FM, and it will be a symmetric component on the positive side. So, it will be FC minus FM to FC. All right. So, this is the USB spectrum, this is the lowest LSB spectrum. So, this is the LSB spectrum, and again just to remind you, USB equals upper sideband, LSB equals the lower sideband, and therefore, what is the big advantage of transmitting only one sideband, that is either the upper sideband or the lower sideband over the double sideband modulation over a system which employs double sideband suppressed carrier modulation. And now you can clearly see that both USB and LSB, if you look at the pass band bandwidth of both USB, the USB passband bandwidth is from FC to FC plus FM, which means it has a passband bandwidth of, which means this scheme has a passband bandwidth of FM and similarly the LSB signal also has a pass FC minus FM to FC, that is it has a passband bandwidth of FM. So, it has a passband signal, it has a passband bandwidth of FM. So, you can clearly see that the double sideband suppressed carrier signal has a passband bandwidth of 2 FM, while both the upper sideband and the lower sideband, which basically any single sideband modulated signal has a passband bandwidth of only FM, and therefore it results in a bandwidth saving of, so from 2 FM you are going to FM, so it results in a bandwidth saving of 50% in comparison to, so depending on the way you look at it, results in a 50% savings, results in a required bandwidth is reduced by a factor of half. So observe that the bandwidth of, so the idea behind, so observe the passband bandwidth of both LSB comma SSB signals equals FM, which is equal to half bandwidth of your DSB or DSB SB signal, implies, which implies that your, I am sorry, this is LSB and USB, which implies that SSB, which is either LSB or USB, which is SSB, which is equal to either, so I am writing this as LSB slash USB. Single sideband can be either LSB, that is a lower sideband, or upper sideband, results in a significant savings in bandwidth. Specifically, how much bandwidth is the bandwidth required in comparison to double sideband modulation is reduced by a factor of half. Therefore, the spectral efficiency doubles, that is spectral efficiency, which is defined as the information content divided by the bandwidth. Since the bandwidth is decreasing by a factor of half while the information content is remaining the same, the spectral efficiency doubles. So, the spectral efficiency implies, this leads to a significant improvement of the this leads to a significant improvement of the so called, we have not defined it precisely, the spectral efficiency, correct, spectral efficiency of system, and also although we have not defined it precisely, you can see the spectral efficiency is approximately basically information. There is a precise way of characterizing the information by the entropy, but we are not looking at that information divided by the bandwidth. Since information is constant and bandwidth is and also let us note that since information of SSB is same as TSB, and however bandwidth of SSB equals half bandwidth of DSB, this implies, so information content is the same, bandwidth is reduced by a factor of half, therefore, spectral efficiency of SSB is twice that of DSB. Therefore, the spectral efficiency of SSB, spectral efficiency equals twice the spectral efficiency of DSB, that is double sideband modulated signal, and this is an important result. So, SSB is a very important scheme, or it is a very efficient scheme because it results in a significant reduction in bandwidth. Precisely how much reduction in bandwidth leads to a decrease of the DSB bandwidth by a factor of half. All right. So, we have seen that if you consider a message signal MT and a DSB, that is double sideband modulated message signal, that is XT, which is given as MT cosine 2 pi FCT. This has two sideband, which is the lower sideband and the upper sideband, and one can therefore transmit, and the DSB signal has a passband bandwidth of 2 FM, but the LSB or the lower sideband signal or the upper sideband signal has only a passband requires a passband bandwidth of FM. Therefore, the bandwidth required in single sideband modulation, that is either LSB or USB, is reduced by a factor of half, decreases by a factor of, right, is reduced by a factor that is the bandwidth required in LSB or USB is half that half the bandwidth that is required in DSP. Therefore, spectral efficiency improves, spectral efficiency doubles. For the same information, since the bandwidth decreases by a factor of, that is bandwidth is half of that of DSB, the spectral efficiency is double that of DSP. Alright. So, we will stop here and look at other aspects, in particular various ways of generation of these SSB, that is single sideband modulated signals, in the subsequent modules. Thank you very much.